There is a strange problem hidden inside the size of the universe. At first, it sounds almost comforting. The universe is huge. It gives galaxies room to drift. It gives stars room to burn. It gives planets room to form in quiet corners of space. But the deeper you look, the less comforting it becomes, because the universe is not just large in the way an ocean is large, or a mountain range is large, or the distance between two countries is large. The universe is so large that distance stops feeling like distance. It becomes time. It becomes isolation. It becomes a wall made from light itself. And the most disturbing part is that this size is not an accident. The universe did not simply become enormous because it had a lot of time to stretch. The story is stranger than that. Space itself expanded. The early universe changed faster than ordinary intuition can follow. Regions that were once close enough to affect each other were pulled so far apart that they may never speak again, not with ships, not with signals, not even with light. Before we go deeper, if you enjoy calm journeys through space, take a moment to subscribe, leave a like, and write a comment telling us where you are watching from and what time it is for you right now. It is a small thing, but it helps Just About Space reach more people who love these quiet, strange questions about the cosmos. Tonight, you are watching the Just About Space channel. Talking about the universe is huge for a reason, and it's terrifying. And to understand why the size of everything feels so unsettling, we have to begin somewhere very small, not with galaxies, not with black holes, not with the edge of the observable universe, but with the space between you and the moon. The moon looks close because the human brain is not designed for astronomy. It hangs in the sky like a bright coin. It seems like something that belongs to our world, something just above the clouds. But the moon is roughly 238,045 miles from Earth on average. If you could somehow drive a car upward at highway speed without stopping, it would take months to get there. If you stacked every planet in the solar system between Earth and the moon, they would almost fit in that single gap. That is the first quiet warning. Even the nearest world is not near in any ordinary sense. Then comes the sun. The sun is about 93 million miles away. Light, moving at about 180 seconds and miles every second, still needs roughly 8 minutes to cross that distance. Every sunrise is slightly old. Every warm beam of sunlight has already spent minutes crossing emptiness before it touches your skin. And the sun is not some remote object at the edge of our neighborhood. It is the center of it. Earth is close to it. Mercury is closer. Venus is closer than we are. Mars, Jupiter, Saturn, Uranus, and Neptune all sit farther out, each orbit opening another layer of distance. By the time you reach Neptune, sunlight is no longer the warm presence we know on Earth. It is faint, thin, distant. Neptune is about 30 times farther from the sun than Earth is, so the sun's light is spread across a much larger sphere by the time it reaches that blue planet. From Neptune, the sun would still be bright, but not familiar. It would look like an extremely intense star, rather than the blazing disk that rules our sky. And yet Neptune is still inside our solar system. That is what the word huge begins to mean. Not that the universe contains big things, not that planets are far apart, but that the first real step outward already breaks the scale of normal thought. If the sun were the size of a grapefruit, Earth would be a tiny speck several meters away. Jupiter would be far across the room. Neptune would be outside the building. And the nearest star would not be in the next room, or across the street, or in another city. It would be thousands of miles away in the same scale model. The nearest star system to us is Alpha Centauri, about 4.37 light-years away. A light-year is not a year of time. It is a distance. The distance light travels in 1 year, and light is the fastest messenger the universe allows. So when we say Alpha Centauri is 4.37 light-years away, we are saying something very specific. We are saying the light arriving from that system tonight began its journey more than 4 years ago. If something happened there right now, we would not know until years later. If humans could travel there with current spacecraft technology, the trip would take tens of thousands of years. The solar system is wide. The gap to the next star is worse. This is where the universe begins teaching a harsh lesson. It is not enough for something to exist. It is not enough for it to be real, or beautiful, or possibly habitable. Distance can make a real place functionally unreachable. A planet around Alpha Centauri could have oceans. It could have continents. It could have clouds, storms, seasons, and alien sunsets. But from Earth, even that nearest stellar neighborhood is a place we can barely touch with light and mathematics. We can observe, estimate, and imagine. We cannot casually go. And Alpha Centauri is only the closest example. The Milky Way contains hundreds of billions of stars. Its disk stretches roughly 100,000 light-years across. That means light itself, moving at the universal speed limit, needs about 100,000 years to cross from one side of our galaxy to the other. Human civilization, from the first cities to today, is only a tiny fraction of that time. A signal sent from one edge of the Milky Way would cross entire histories before reaching the other side. Species could rise, build monuments, invent tools, look up at the sky, disappear, and become fossils before a single message finished crossing their own galaxy. That is just one galaxy. Beyond the Milky Way are other galaxies, not scattered like nearby islands in a small pond, but spread across a cosmic ocean so large that even our most familiar galactic neighbor, Andromeda, is about 2.5 million light-years away. The light we see from Andromeda left before modern humans existed. It was already crossing space while ancient ancestors on Earth were still far from anything we would recognize as civilization. And Andromeda is close. In cosmic terms, it is part of our local neighborhood. It is gravitationally bound to us. The Milky Way and Andromeda are slowly moving toward each other and will eventually merge billions of years from now. But outside this local group, the universe expands. Galaxy groups and clusters are carried away from one another by the stretching of space itself. This is the first reason the universe's size becomes frightening. The distances are not simply large. They are active. They are changing. They are not quiet gaps waiting to be crossed. Space itself is part of the story. To see why, imagine drawing dots on the surface of a balloon. If you inflate the balloon, the dots move apart, not because they are crawling across the rubber, but because the rubber between them is stretching. That image is imperfect because the universe is not expanding into some larger room outside itself, but it gives the basic idea. Galaxies are not generally flying through space from a central explosion. Instead, on the largest scales, the space between galaxy clusters is expanding. This matters because it changes the meaning of distance. In ordinary life, distance is a measure of how far you must travel. In cosmology, distance can also tell you how much the universe has changed while light was traveling. A galaxy can emit light when it is much closer, and by the time that light reaches us, the galaxy can be much farther away. The universe does not wait politely for its own light to arrive. It stretches while the light is moving. That is why the observable universe is larger than 13.8 billion light-years in radius, even though the universe is about 13.8 billion years old. At first, that sounds impossible. If nothing travels faster than light, how can we see objects that are now much farther away than 13.8 billion light-years? The answer is expansion. The light from the most distant regions has traveled for billions of years, but during that journey, space itself expanded. The place that emitted that ancient light is now far beyond the simple distance you would expect from travel time alone. The observable universe today has a radius of roughly 46 billion light-years, not because light broke the speed limit, but because the ruler grew while the light was on its way. That single idea should make the universe feel different. We do not live inside a static container filled with galaxies. We live inside an evolving geometry. The scale of the cosmos is not only a number, it is a history. Every distant galaxy is a message from a different time. Nearby stars show us the recent past. Nearby galaxies show us deeper history. The farthest galaxies show us the young universe. And the cosmic microwave background, the oldest light we can see directly, shows us the universe when it was only about 380,000 years old. To human ears, 380,000 years sounds ancient. In cosmic history, it is infancy. Before that time, the universe was too hot and dense for light to travel freely. Electrons and atomic nuclei were not yet settled into neutral atoms. Photons scattered again and again through a glowing plasma. Space was not dark, but it was opaque. It was like being inside a fog made from fire. Then the universe expanded and cooled. Electrons joined with nuclei. Neutral atoms formed. Light could finally travel long distances without constantly hitting charged particles. That released the cosmic microwave background, a faint afterglow that still surrounds us from every direction. When we detect that radiation today, we are not looking at stars. We are not looking at galaxies. We are looking at a surface in time, the moment the universe became transparent enough for light to move freely. And even that ancient light does not show us the whole universe. It shows us the edge of what has had time to reach us. This is one of the deepest traps in thinking about cosmic size. The observable universe is not the universe. It is the part of the universe from which light has reached Earth so far. If something is beyond that horizon, it may be real. It may contain galaxies, stars, planets, and histories, but its light has not had enough time to arrive. The horizon is not a wall made of matter. It is not a shell floating somewhere in space. It is a limit created by time, light speed, and expansion. If you stood on a planet in a galaxy near the edge of our observable universe, you would not see Earth sitting at the center of everything. You would see your own observable universe around you. Some regions visible to you would be invisible to us. Some regions visible to us would be invisible to you. Every observer has a cosmic horizon. That means our view is not special, it is local. And that is terrifying in a quiet way, because it means the universe can be much bigger than the universe we can ever map. Possibly far bigger, possibly infinite. Scientists do not know the full size of the entire universe. Measurements suggest that on the largest observable scales, space appears very close to flat. In cosmology, flat does not mean thin, like a sheet. It means that the geometry of space, as far as we can measure, behaves very much like ordinary Euclidean geometry. Parallel lines stay parallel. Large triangles add up in the expected way. The curvature, if it exists, is too slight for us to clearly detect within the observable patch. If the universe is exactly flat and has the same basic properties everywhere, it may be infinite. If it is slightly curved in a way too subtle for us to detect, it could be finite but much larger than our observable region. Either way, the part we see may be only a small piece of the whole. This is where the title begins to take shape. The universe is huge for a reason. Part of that reason lies in its beginning. Not the beginning in a simple explosion sense. The Big Bang was not a bomb going off in empty space. It was not matter flying outward from a central point into a pre-existing void. The Big Bang describes an early hot, dense state of the universe itself, followed by expansion. Space was not the stage where the event happened. Space was part of what was changing. In the earliest fraction of a second, according to the inflationary idea, the universe may have expanded at an astonishing rate. This period is called cosmic inflation. It is one of the most important concepts in modern cosmology because it helps explain several strange features of the universe we see today. Inflation is not just the claim that the universe expanded. The universe is still expanding now. Inflation refers to an extremely brief, extremely rapid expansion in the early universe. During that moment, tiny regions could have been stretched to enormous scales. A patch of space smaller than something subatomic could become vastly larger than the observable universe. That sentence is difficult to hold in the mind. It sounds like fantasy, but it was proposed to solve real scientific puzzles. One puzzle is called the horizon problem. When scientists measure the cosmic microwave background, they find that it has nearly the same temperature in every direction. Not perfectly the same. There are tiny differences, and those tiny differences are extremely important. But overall, the ancient afterglow is astonishingly uniform. Why is that strange? Because regions on opposite sides of the sky are so far apart that, in a simple, non-inflationary picture, they should never have been able to exchange heat or information before releasing the light we see today. They should not have had time to come into thermal agreement. And yet they match with extraordinary precision. It is like finding two rooms on opposite sides of a city at the exact same temperature, even though no air, no pipes, no wires, and no people ever connected them. Inflation offers a solution. Perhaps those distant regions were once close together. Perhaps they had time to even out when the universe was much smaller. Then inflation stretched them apart so dramatically that they now appear on opposite sides of our observable sky. What looks impossibly coordinated today may be the fossil of an ancient closeness. Another puzzle is the flatness problem. The universe appears very close to geometrically flat. But in standard cosmology, a universe must be tuned very precisely in the early moments to remain so flat today. If the density had been even slightly different, space could have curved strongly, either collapsing too soon or expanding in a very different way. Inflation smooths that out. When something expands enormously, curvature becomes harder to notice. A small patch of a sphere can look flat if you zoom in enough. Earth is round, but a field beneath your feet appears flat. In the same way, inflation could have stretched space so much that any original curvature became nearly undetectable inside our observable region. That gives the universe part of its enormous scale, not because it needed to be spacious for us, not because it was designed as an empty arena, but because the early physics may have stretched a small region into something almost unimaginably large. And this brings us to one of the most unsettling ideas in science. The universe we can observe may be a tiny bubble of order inside something vastly beyond measurement. Inflation may have ended in the region that became our observable universe. But in some versions of the theory, inflation may continue elsewhere. Other regions could stop inflating at different times. This idea leads to the possibility of a much larger cosmic structure, sometimes called eternal inflation or a multiverse, though these ideas remain speculative and difficult to test. We do not need to rely on speculation to feel the terror of the scale. The observable universe alone is enough. Consider what we actually see when we look deep into space. We see galaxies arranged in a great cosmic web. They are not spread randomly like dust thrown into the air. On the largest scales, galaxies gather along filaments, cluster at intersections, and leave enormous voids between them. These voids can stretch for hundreds of millions of light years. They are not completely empty, but compared with galaxy-rich regions, they are staggeringly sparse. The universe is not like a city packed evenly with lights. It is more like a vast network of glowing threads separated by dark caverns. Gravity built this web from small beginnings. Those tiny temperature differences in the cosmic microwave background were not meaningless noise. They were the seeds of structure. Slightly denser regions attracted more matter. Over time, they grew. Gas fell in. Dark matter formed invisible scaffolding. Stars ignited. Galaxies assembled. Clusters formed. Voids emptied out as matter flowed toward denser regions. The result is beautiful from far away, but eerie when you imagine crossing it. If you could leave the Milky Way and travel through intergalactic space, most of your journey would not be between stars. It would be through darkness far emptier than anything inside our galaxy. The nearest stars would fall behind. The glow of the Milky Way would shrink into a flattened mist. Ahead, another galaxy might slowly brighten, but the crossing would be measured not in years or centuries or even typical human civilizations, but in millions of years if limited by anything close to known physics. The universe is huge not only because there are many galaxies, but because the spaces between them are also huge. The emptiness is part of the architecture. This can feel wasteful, as if the universe built more room than it needed. But physics does not work from human ideas of efficiency. Gravity amplifies small differences. Expansion increases separations. Radiation cools as space stretches. The universe is not trying to make itself easy to explore. It is following rules that produce scale as a natural consequence. That is a very different kind of fear from a monster or a collision or a supernova. It is the fear of a system that does not know you are here. A system where most places are not dangerous because they are violent, but because they are unreachable, unbreathable, lightless, and indifferent. The size of the universe also controls what can influence what. On Earth, almost everything around you is connected by fast signals. You can speak to someone across the world in a fraction of a second through modern technology. Weather systems move across oceans. Light from a lamp reaches a wall instantly to your senses. Human intuition grows inside a world where information usually seems immediate. The cosmos is different. There is no universal now that everyone can observe together. When you look at the moon, you see it about 1.3 seconds in the past. When you look at the sun, you see it about 8 minutes in the past. When you look at Jupiter, depending on its position, you see it tens of minutes in the past. When you look at the Andromeda Galaxy, you see it millions of years in the past. A telescope is not only a magnifying tool, it is a time machine with strict limits. It never shows the present of a distant object. It shows the moment when light began its trip. This means the universe is layered by delay. Space and time are stitched together in the act of seeing. The farther we look, the older the universe becomes. And when we reach the deepest visible layers, we are not seeing stars as they are now. We are seeing galaxies before Earth existed, before the sun formed, before heavy elements had fully spread through the cosmos. The universe's size turns observation into archaeology. Every photon is a fossil, but this archaeology has a boundary. We can only dig as far as light has reached us, and as far as the universe allows clear signals to pass. Beyond the cosmic microwave background, direct light cannot show us earlier ordinary images, because the universe before that was opaque. Scientists can still infer earlier conditions using physics, particle experiments, cosmic structure, gravitational waves in principle, and the patterns frozen into the microwave background. But we cannot simply take a photograph of the first instant. The universe hides its birth behind a glowing curtain. And because it is so large, much of what exists beyond our horizon may never enter the story we can verify. This is why the size of the universe is connected to humility. Not the soft, poetic kind, but the hard, scientific kind. Our instruments are extraordinary. They can measure faint signals from billions of years ago. They can detect galaxies whose light has been stretched into infrared. They can map temperature variations in ancient radiation smaller than a fraction of a degree. And still, the cosmos is larger than our access. The universe gives us evidence, not full possession. It offers patterns, not total visibility. It lets us reconstruct the past, but not stand outside the hole and look down. There is no balcony beyond the universe. There is only perspective from within. To understand why that perspective is limited, we need to think about the speed of light more carefully. In science fiction, light speed is often treated like a fast highway speed. Something difficult, maybe impossible for current technology, but still a number to beat. In real physics, light speed is deeper than that. It is not merely the speed of light. It is the speed of causality. It is the maximum speed at which information, influence, and cause and effect can travel through space. If a star exploded 1,000 light years away, Earth could not know for 1,000 years. Not because our telescopes are weak, not because we failed to look, but because the information physically has not arrived. There is no shortcut inside ordinary space-time that lets the news get here sooner. This creates a cosmic map unlike any map on Earth. On Earth, a map is mostly about where things are. In cosmology, a map is about what parts of the universe can be causally connected. Can light from there reach here? Could a signal sent now ever arrive? Did two regions ever have time to influence each other? These questions matter as much as location. The vastness of the universe is therefore not only spatial, it is causal. It determines what can know what. That may be the most important difference between a big universe and a terrifyingly big universe. A merely big universe would be hard to cross. A causally limited universe contains places that may be forever outside contact. And yet the first half of the story is not only about separation. It is also about why the universe needed scale to become interesting at all. If the universe had not expanded, it would have remained hot and dense. Matter would not have settled into atoms in the same way. Light would not have traveled freely. Stars and galaxies would not have formed as we know them. Expansion cooled the universe. Cooling allowed structure. Structure allowed stars. Stars forged heavier elements. Those elements later formed planets, oceans, rocks, atmospheres, and eventually living chemistry. The universe had to grow in order to become transparent. It had to become less uniform in order to build galaxies. It had to create enormous regions of low density so gravity could gather matter elsewhere. In that sense, the size is not an extra feature, added after the important parts. The size is part of the process that made the important parts possible. A small, cramped universe would not necessarily be a friendly universe. If matter were packed too tightly, radiation would remain intense, collisions would be common, stable systems might be impossible, and the quiet conditions needed for planets could fail to last. Life, at least life like ours, needs local calm. It needs a star that can burn steadily for billions of years. It needs planets that can orbit without constant disruption. It needs chemistry that is not being torn apart every moment by extreme heat. The universe's emptiness can look like loneliness, but emptiness also protects. The distance between stars helps keep planetary systems stable. The space between galaxies allows structures to evolve. The cooling caused by expansion allows atoms to exist. The darkness between lights is not just absence. It is part of the environment where complexity can survive. This does not make the size less frightening. It makes it stranger. Because the same vastness that allows life to exist also prevents that life from easily reaching most of what exists. The universe gives with one hand and withdraws with the other. To see this tension, think about Earth. Earth sits in a relatively calm region around an ordinary star. The Sun is not the largest star, not the hottest, not the oldest, not the most dramatic. It is stable enough. That stability matters more than grandeur. For billions of years, it has provided energy at a level Earth could use without being destroyed. Our planet formed with rock, water, carbon, nitrogen, oxygen, metals, and a magnetic field. It has a large moon that may help stabilize its axial tilt. It has plate tectonics, an atmosphere, and a long chemical history. All of that happened in one small location inside one spiral galaxy among billions. The universe had to be old enough for earlier stars to live and die, scattering heavy elements into space. The first stars mostly formed from hydrogen and helium. They could not build rocky planets like Earth from nothing. Heavy elements had to be forged in stellar interiors and explosive events, then mixed into later generations of gas clouds. So, Earth is not just located in space. It is located in cosmic time. It could not have existed at the very beginning. The universe had to expand, cool, form stars, recycle matter, build galaxies, and wait. The ingredients of our bodies required previous cosmic history. The carbon in cells, the oxygen in water, the iron in blood, the calcium in bone, all came from processes older than Earth. The size of the universe gave those processes room and time to happen. But once again, the price is distance. The heavy elements that make worlds possible were scattered across space by stars that died long before the sun was born. The galaxy mixed them slowly. New clouds collapsed. New stars formed. Planets assembled. This is not a fast, tidy process. It is huge, messy, gravitational, violent, and slow. The universe is not a machine built at human scale. It is a process unfolding across billions of years and billions of light years. That is why asking why the universe is huge is not the same as asking why a room is large. A room is built for a purpose. The universe is not known to be built for us. Its size emerges from expansion, physics, initial conditions, gravity, dark matter, radiation, and time. The terrifying part is that we are a byproduct capable of noticing the scale. We can measure enough to feel trapped by what we measure. Now, let us go back to the beginning again, but more slowly. The observable universe started from a state that was hot, dense, and expanding. Scientists can describe much of its early evolution with remarkable precision, but the closer we get to the earliest moments, the more our current theories are pushed toward their limits. General relativity describes gravity and the large-scale structure of space-time. Quantum physics describes the behavior of particles and fields at tiny scales. In the very earliest universe, both should matter intensely, but a complete theory joining them is still beyond us. So when we speak about the beginning, we must be careful. We are not pretending to know everything. We are following evidence as far as it can currently take us. That evidence says the universe was once far hotter and denser than it is now. We know this because distant galaxies are moving away from us in a pattern consistent with expansion. We know this because the cosmic microwave background exists as cooled ancient radiation. We know this because the early universe produced light elements in proportions that match observations. Hydrogen, helium, and traces of lithium carry the chemical fingerprint of a hot early cosmos. The universe expanded. As it expanded, it cooled. As it cooled, new forms of structure became possible. At first, the universe was too energetic for atoms. Later, atoms formed. Much later, gravity pulled gas into the first stars. Those stars changed everything. They produced light, heavier elements, and the first steps toward the complex universe we see today. But before stars, before galaxies, before planets, the scale had already been shaped by expansion. Inflation is the key early chapter in that shaping. It is difficult to exaggerate how extreme inflation is, because every ordinary comparison fails. We can say a tiny region expanded enormously. We can say it happened in a fraction of a second. We can say it may have stretched quantum fluctuations into the seeds of galaxies. But each sentence is too calm for what it describes. Imagine marks on a surface being pulled apart so quickly that neighboring points become cosmically separated before anything can cross between them. Imagine microscopic irregularities being stretched until they become the blueprint for future clusters and voids. Imagine the future map of galaxies being influenced by tiny fluctuations from a time before atoms existed. That is the kind of idea inflation gives us. It is not merely that the universe became big. It is that the universe became big in a way that preserved tiny differences, turning them into cosmic architecture. This is one of the reasons the universe is not perfectly smooth today. If matter had been distributed with absolute uniformity, gravity would have had no preferred places to gather. The universe might have remained a thin, cooling fog with no stars, no galaxies, no planets, no chemistry, no observers. But the early universe had small variations. Some regions were slightly denser than others. Gravity amplified those differences over time. A denser region attracted more matter. More matter deepened the gravitational pull. That drew in still more matter. Given enough time, small beginnings became enormous structures. This is how the universe built contrast. Not instantly, not magically, but through patient gravitational growth. In this first half of the story, the important thing is not dark energy yet. That will become more important later when we talk about the future and the unreachable universe. For now, we are looking at the old expansion, the early stretch, the cooling, and the formation of structure. Because the universe's huge scale is not only about where things are now, it is about how anything had enough time and room to form at all. Think of the cosmic microwave background again. It is often shown as an oval map covered with tiny color variations. To a casual viewer, it can look like a strange weather map, but it is one of the most important images humanity has ever made. It shows the early universe with small differences in temperature and density. Those differences are not galaxies yet. They are not stars. They are the seeds of later structure. When you look at that map, you are seeing the universe before the Milky Way, before the sun, before Earth, before oceans, before eyes, before anyone could wonder about the sky. The map is almost smooth. Almost. That word matters. If it were perfectly smooth, structure would struggle to form. If it were wildly uneven, the universe might be too chaotic. Instead, it had tiny variations at the right level for gravity to work over time. Those variations, stretched and preserved from the early universe, became the starting pattern for the cosmic web. This is part of the reason the universe feels both ordered and enormous. The biggest structures we see today grew from faint early imprints. The present vastness remembers the first moments. The universe is huge, but it is not shapeless. It has a history written into its size. When galaxies formed, they did not appear everywhere at once in isolation. They formed where matter could gather. Dark matter, which does not emit light but exerts gravity, played a central role. It formed large halos that helped pull ordinary matter inward. Gas collected, cooled, and eventually formed stars. Galaxies grew through mergers, accretion, and internal star formation. The space between galaxies did not vanish. It expanded. Matter became concentrated in some places and sparse in others. The universe grew more structured as it grew larger. This is a strange point. Expansion makes the universe thinner on average, but gravity makes certain regions denser. The universe can become emptier overall while building islands of enormous complexity. It can stretch the background while allowing galaxies to gather in knots and filaments. That tension gives the cosmos its character. Expansion separates, gravity gathers, radiation cools, stars ignite, matter cycles, voids widen, filaments sharpen. No single phrase can capture it, and that is exactly why a good script cannot repeat the same emotional sentence again and again. The universe is not only big and scary, it is big in different ways for different reasons. It is big because of early inflation. It is big because expansion continues. It is big because light needs time. It is big because gravity builds structure slowly. It is big because emptiness and complexity grow together. Each of those kinds of size feels different. The size between Earth and the Moon feels like engineering difficulty. The size between stars feels like historical separation. The size across the Milky Way feels like civilizational impossibility. The size between galaxy clusters feels like cosmic isolation. The size beyond the observable horizon feels like permanent ignorance. And the size produced by inflation feels like something almost outside human imagination. This is how we should understand the title. The universe is huge for a reason, but not one simple reason. It is huge because the same physical processes that allowed it to cool, flatten, smooth, seed structure, and later form galaxies also made it vast beyond reach. The terror is not a single jump scare. It is a chain of consequences. Now let us pause at the idea of emptiness because it is easy to misunderstand. When people hear that space is empty, they may imagine a blank nothing. But cosmic emptiness is not simple nothingness. Intergalactic space can contain thin gas, dark matter, magnetic fields, radiation, neutrinos, cosmic rays, and faint light from distant sources. Even the emptiest voids are part of the universe's structure. They have history. They have shape. They influence how matter flows around them. But compared with a planet, a star, or even the space inside a galaxy, cosmic voids are astonishingly empty. A human body is dense with atoms. Earth's atmosphere is packed with molecules. A star is a furnace of plasma. A galaxy contains stars, gas, dust, dark matter, and black holes. But a cosmic void can stretch across hundreds of millions of light years with very little luminous matter inside it. Imagine traveling through one. No nearby stars filling the sky. no bright spiral galaxy overhead, no familiar Milky Way band. Only distant island universes, faint and scattered, seen from a place where the cosmos has thinned almost to silence. This is not the same fear as standing near a volcano or falling into a black hole. It is the fear of absence. A void does not attack, it does not chase, it simply gives almost nothing back. And yet voids are not mistakes. They are what happens when gravity pulls matter away into denser regions over cosmic time. The cosmic web needs voids as much as it needs filaments. If everything were evenly packed, there would be no web, no clusters, no dramatic contrast. The universe becomes interesting by becoming uneven. It becomes beautiful by becoming mostly empty. This is the uncomfortable truth behind cosmic scale. The same emptiness that makes galaxies stand out also makes them lonely. A spiral galaxy is stunning, partly because it shines against darkness. A star cluster is beautiful, partly because the surrounding space is black. The Milky Way arches across a rural sky because the background is dark enough for its glow to be seen. If the universe were filled uniformly with blazing light, there would be no night, no contrast, no quiet depth. But from the standpoint of life trying to travel, that darkness is a barrier. It is distance made visible. It is the universe telling us how much is between the islands. Another way to feel this scale is to follow a single photon. Imagine a photon released from a young galaxy more than 13 billion years ago. It begins its journey when the universe is still young. The first large galaxies are assembling. Heavy elements are still rare compared with today. There is no Earth. There is no sun. There is no solar system, no blue planet, no oceans, no forests, no human eyes waiting to receive the light. The photon travels through expanding space. It does not grow tired. A photon does not age in the human sense. But the universe around its path changes. Space stretches. The wavelength of the photon stretches with it. What may have begun as ultraviolet or visible light becomes infrared by the time it reaches modern telescopes. The photon carries the past, but it arrives altered by the journey. This is redshift. It is not just a color change. It is a record of cosmic expansion. The more space has expanded during the light's journey, the more stretched the light becomes. Astronomers use that stretching to estimate how far back in time they are looking and how much the universe has grown since the light was emitted. So distance is written into the light itself. The universe marks its own expansion on every ancient signal. This makes deep astronomy different from ordinary photography. A photograph of a mountain shows a place as it was moments ago. A deep field image of galaxies shows different ages of the universe in the same frame. One galaxy may be 1 billion years in the past. Another may be 5 billion. Another may be more than 13 billion. They appear together on an image, but they do not belong to the same moment. A telescope can put them side by side visually. Reality did not put them side by side in time. That is why the universe's hugeness can be misleading even when we see it. The sky flattens time into a view. We look up and think everything is simply out there. But every point of light is a different delay. The night sky is not a ceiling. It is a layered archive. And the deeper the archive goes, the less familiar the universe becomes. The early galaxies were not simply smaller versions of modern galaxies. They lived in a younger cosmos. Their stars formed from less chemically enriched gas. Their central black holes may have grown rapidly. Their shapes could be chaotic. Their light was born in an environment still building the structures we take for granted. When we look far enough, we do not just see distant places. We see the universe before it learned to look like itself. That is another reason size matters. Without enormous distances, there would be no deep look-back time. The universe's scale gives us a way to see its own history. If everything were nearby, every view would show nearly the same cosmic age. Because the universe is vast, its past is spread across the sky. This is beautiful, but it has a cost. The farther back we look, the fainter the signals become. Light spreads out, expansion stretches it. Dust can absorb it. Instruments must be cooled, shielded, calibrated, and placed beyond Earth's atmosphere to catch what little remains. We are not reading a bright open book. We are trying to recover faded ink from pages carried across billions of years. Now zoom outward again. The Milky Way and Andromeda are part of the Local Group, a collection of more than 50 galaxies bound together by gravity. Many are dwarf galaxies, small companions orbiting larger systems. This group is large by human standards, but it is only a small knot in a much bigger pattern. The Local Group lies near the edge of the Virgo supercluster, and on even larger maps, it is often described as part of an immense flow of galaxies called Laniakea. These names help us organize the cosmic neighborhood, but they can also be misleading. A supercluster is not like a solid object. It is not a single island with firm borders. It is a region of gravitational influence, motion, and structure inside the larger cosmic web. At these scales, the universe becomes less like a collection of objects and more like a pattern of flows. Galaxies fall toward dense regions. Clusters pull on surrounding matter. Voids expand relative to the filaments around them. The map is alive with motion, but the motion is slow beyond imagination. When we say a galaxy cluster is millions or billions of light years away, we are using a phrase that sounds simple but hides a brutal fact. Even at the speed of light, a signal would cross that distance over a time longer than many stars live. At ordinary spacecraft speeds, the journey becomes effectively meaningless. Not hard, not expensive, not risky. Meaningless in the sense that the destination belongs to a different scale of reality. Human beings are good at extending reach. We crossed oceans. We built aircraft. We sent probes beyond the planets. But the universe introduces distances where the old pattern breaks. Exploration no longer scales smoothly. Crossing a sea is not a smaller version of crossing intergalactic space. The difference is not degree, it is category. That category difference is important for this video. The universe is huge enough to change the meaning of ambition. On Earth, a difficult place can become accessible with better tools. Mountains become climbable, deserts become navigable, oceans become routes. In space, some targets do become accessible with better tools. The Moon, Mars, asteroids, perhaps one day the outer planets. But beyond a certain scale, technology collides with the structure of space-time itself. A civilization might become powerful. It might build faster probes, enormous telescopes, self-sustaining habitats, fusion drives, laser sails, or generation ships. It might spread through parts of its galaxy over long ages. Yet the observable universe contains far more than any galaxy. An expansion keeps changing the cosmic map. This is why scale is not just scenery, it is destiny. The universe's size decides what any civilization can realistically share, reach, or remember. A species could become brilliant and still remain local. It could understand galaxies it will never touch. It could name structures that will never know it exists. There is a quiet sadness in that, but there is also a scientific clarity. The cosmos is not arranged around the convenience of observers. Observers arise inside the cosmos and then discover the rules after the fact. This also changes how we should think about the word center. People often ask where the center of the universe is. The question feels natural because explosions have centers, rooms have centers, and maps often have central points. But the expanding universe is not like debris flying away from one location in space. On large scales, every observer sees distant galaxies receding. Every location can describe itself as being at the center of its observable universe, because the observable universe is defined by what light has reached that observer. Earth is not the center of the whole universe. It is the center of our view. That distinction is subtle, but it matters. The cosmic horizon surrounds us because we are looking outward from here, not because the universe was built around us. A distant civilization would have its own horizon. Its map would overlap with ours in some regions and differ in others. It might see galaxies forever hidden from us, while missing galaxies we can see. There may be no privileged central seat. There may only be countless local windows, and each window is limited by the same rules: finite light speed, cosmic age, expansion, and opacity in the early universe. This makes the universe feel less like a stage and more like an ocean in fog. You can study the water around you. You can infer storms beyond the mist. You can receive waves that traveled from far away. But you cannot step outside the fog and inspect the entire sea at once. That is the first half of the fear, not destruction, limitation. This leads naturally to a question that haunted astronomers long before modern cosmology. If the universe is filled with stars, why is the night sky dark? This is often called Olbers's paradox. In an infinite, static, eternal universe filled evenly with stars, every line of sight should eventually end on the surface of a star. The night sky should be bright, perhaps as bright as a stellar surface. But it is not. The night sky is dark. The solution tells us something profound. The universe is not static and eternal in the old simple sense. It has a finite age, it expands, and light from very distant regions is stretched and weakened. Many stars are too young, too far, too redshifted, or beyond our observable horizon. The darkness of the night sky is evidence of cosmic history. Night itself is a clue. When you step outside and see darkness between stars, you are seeing the effects of expansion, finite light travel time, and the evolving universe. The black spaces are not empty of meaning. They are cosmology written across the sky. This is another reason the universe's size becomes disturbing. It hides an ordinary experience. You do not need a giant telescope to encounter the problem. The darkness above your house already contains it. Every night, the universe quietly shows you that it has an edge to what can be seen. Not an edge to what exists, an edge to what has reached us. The difference matters. Now, if we think about the universe from the perspective of information, the situation becomes even stranger. We often imagine that better technology will eventually reveal everything. Build bigger telescopes, launch more advanced observatories, detect fainter signals, and slowly the unknown will shrink. Technology does shrink some unknowns. It has revealed planets around other stars, black holes, gravitational waves, early galaxies, dark matter effects, and the afterglow of the Big Bang. Future telescopes will reveal even more. They may detect biosignatures in exoplanet atmospheres. They may map dark matter with greater precision. They may find the first generation of stars. They may constrain inflation more tightly. But technology cannot erase every horizon. A horizon is not the same as poor vision. If light has not arrived, no telescope can collect it. If expansion prevents a future signal from reaching us, no antenna can receive it. If a region is causally disconnected, it is not merely hard to observe. It is physically outside contact. That is why the huge universe is more unsettling than a dark room. A dark room can be lit. A cosmic horizon may remain. The universe is not hiding everything, because our instruments are primitive. Some things are hidden because space-time works that way. This is where the phrase, "for a reason," should not be misunderstood. It does not necessarily mean purpose in a human sense. It means consequence. It means the universe's size follows from the physics of expansion and structure formation. It means vastness is not decoration. It is woven into the way the cosmos became what it is. If inflation happened, it stretched space dramatically. If expansion continued, distances grew. If light has a finite speed, observation became limited. If gravity needed time to build galaxies, the universe had to age. If heavy elements required previous stars, rocky planets came late. If life needs stability, it benefits from separation. One reason leads to another. The universe is huge because the story that produces observers is long, layered, and spread across scales that dwarf the observers themselves. That is not comforting, but it is coherent. And coherence can be more frightening than chaos. A chaotic universe might feel random and impossible to understand. Our universe, at least in many ways, can be understood. Its largeness follows patterns. Its history leaves evidence. Its radiation cools according to expansion. Its galaxies cluster under gravity. Its background light carries ancient imprints. Its distances obey relationships that can be measured. The terror comes from understanding enough to realize how much the understanding implies. We can calculate the distance to galaxies we will never visit. We can measure the expansion that carries clusters away. We can detect ancient light from a time before stars. We can estimate the age of the universe and still not know whether the whole is finite or infinite. Knowledge does not always make the universe smaller. Sometimes it makes the scale sharper. A child looking at the night sky may feel wonder because there are many stars. An astronomer looking at the same sky knows that most stars visible to the eye are only nearby members of one galaxy, that the galaxy is one among billions, that many galaxies are moving away, that some regions are forever beyond view, and that the darkness between stars carries the signature of cosmic expansion. The view did not change, the meaning did. That is what this first half is really about, not the final fate of the universe, not yet, but the origin of cosmic scale and the way that scale changes every simple question. How far away is the next star? Far enough that human lifetimes become too small. How wide is the galaxy? Wide enough that light needs longer than recorded human history to cross it many times over. How large is the observable universe? Large enough that its radius today is tens of billions of light years because space expanded while light traveled. How large is the whole universe? We do not know. And that answer may be the most honest one in cosmology. We do not know does not mean we know nothing. It means the evidence has a boundary. It means our observable patch is finite, even if reality may not be. It means the universe is not obligated to fit inside the reach of our instruments. This is why the beginning of the universe's hugeness is already terrifying before we even discuss its future. Because even in the past, the cosmos was arranging a scale that would later limit every observer inside it. The early expansion that helped make the universe smooth also stretched regions beyond contact. The cooling that allowed atoms also created a cosmos where light carries history slowly. The gravitational growth that formed galaxies also left immense voids. The stellar generations that built planets required billions of years. The conditions that allowed Earth required a vast background of time, distance, and previous cosmic change. We are not separate from that vastness. We are made from it. But being made from the universe does not mean we can reach all of it. That is the contradiction at the heart of this story. The same universe that produced minds capable of asking cosmic questions also placed those minds inside a horizon. And as we move into the second half, that horizon becomes even more important. Because the universe is not only huge because of what happened long ago, it is still becoming more unreachable. Galaxies beyond our local group are not simply waiting in the distance. On the largest scales, they are receding. The expansion of space is not finished. Dark energy appears to be accelerating that expansion. The cosmic web we see today is not a permanent neighborhood. Over immense time, more and more galaxies will slip beyond practical contact. Their light stretched, faded, and delayed until the universe visible to future observers becomes far emptier than the one we see now. So the first half of the answer is this. The universe became huge because expansion, inflation, cooling, gravity, and time made it huge. But the second half is worse, because its size is not only a memory of the beginning, it is a warning about the future. Because the universe is not only large in the way an ocean is large, or a desert is large, or a mountain range is large when you stand in front of it and feel your body become tiny. The universe is large in a stranger way. Its size changes what can ever happen inside it. It decides which places can exchange light, which galaxies can feel each other's gravity, which civilizations could ever know about each other, and which parts of reality are already beyond every possible journey. This is where the story becomes more unsettling. If the universe were merely huge, then its size would be a challenge. It would be difficult, but not necessarily final. You could imagine a civilization patient enough, advanced enough, or long-lived enough to cross it. You could imagine ships moving for millions of years, or machines sleeping through the dark between the stars, or probes using every star as a stepping stone until the map slowly filled in. But modern cosmology gives us a colder answer. The size of the universe is not just a distance problem, it is a horizon problem. There are places that are not simply far away. They are separated from us by the future behavior of space itself. Even if a beam of light left them now, it may never reach us. Even if we could somehow build a spacecraft that traveled as close to light speed as physics allows, there are galaxies we could never visit, not because our engines are weak, but because the stage beneath the journey is stretching faster than the journey can win. That is the difference between a big universe and a terrifying one. A big universe makes you feel small. An expanding, accelerating universe tells you that smallness is not the whole problem. The problem is that the exits are closing. To understand why, we need to return to something that sounds simple, but is one of the easiest ideas in cosmology to misunderstand. The galaxies are moving away from us. When astronomers first discovered this, it was tempting to picture an explosion, a central blast, matter thrown outward into an empty space around it, galaxies flying away like sparks from a firework. But that picture is wrong. The Big Bang was not an explosion inside space. It was an expansion of space. There was no central point where everything began spreading into a pre-existing emptiness. Every region of the early universe was once hotter, denser, and closer together. Every region expanded. Every observer in any ordinary galaxy would see distant galaxies moving away. This is why the universe has no center in the usual sense. The expansion is not happening from one special location. It is happening everywhere. A common way to imagine this is to picture dots drawn on the surface of a balloon. As the balloon inflates, the dots move farther apart. No dot is the center of the surface. Each dot sees other dots receding. The surface itself is stretching. The real universe is not a two-dimensional balloon surface, and the analogy eventually breaks. But it helps with the essential idea. Space can grow. Distances between unbound galaxies can increase because the geometry between them changes. This means that when we say a distant galaxy is receding, we do not always mean it is traveling through space like a rocket. Often, we mean the amount of space between us and that galaxy is increasing. And on very large scales, that distinction matters. A rocket moving through space is limited by the speed of light. It cannot locally outrun light through the space around it. But the expansion of space itself is not a rocket moving through space. It is the metric, the measuring grid, changing over cosmic time. So, two very distant galaxies can become separated at a rate greater than the speed of light without either one locally breaking the speed limit. Nothing is racing through its own neighborhood faster than light. The distance between neighborhoods is growing. That is already strange enough. But the truly unsettling part is that the expansion is not merely continuing. It appears to be accelerating. For much of the 20th century, many scientists expected gravity to be slowing the expansion down. That would make intuitive sense. Every galaxy pulls on every other galaxy. Every cluster, every cloud of dark matter, every huge structure in the cosmic web adds a little gravitational attraction. If the universe began expanding long ago, then gravity should act like a brake, gradually reducing the speed of that expansion. The question was how strong the braking would be. Would the universe expand forever, slowing but never stopping? Would it eventually stop expanding and collapse back inward? Or would it balance almost perfectly on the edge? For a long time, these seemed like the obvious possibilities. Then observations of distant supernovae changed the story. Astronomers used Type Ia supernovae as cosmic distance markers. These exploding stars are not perfect candles, but they are useful enough that, when measured carefully, they can reveal how far away their host galaxies are. By comparing those distances with the redshifts of the galaxies, scientists could reconstruct how the expansion rate had changed over time. The result was surprising. The expansion was not slowing in the way people expected. It was speeding up. Something was causing space to expand faster over time on the largest scales. We call that something dark energy. That name sounds dramatic, but it is also honest. It is dark because we do not see it directly as light. It is energy because it behaves like a property of the universe that affects expansion. But the name does not mean we fully understand what it is. It could be related to the cosmological constant, a kind of energy built into the vacuum of space itself. It could be something more dynamic, changing over time. It could even point toward a deeper problem in our understanding of gravity. At the moment, the simplest model works remarkably well. In that model, dark energy is nearly constant throughout space. As the universe expands, ordinary matter becomes more diluted. Galaxies spread out, gas thins, radiation stretches to longer wavelengths. But the dark energy associated with space itself does not dilute in the same way. If you create more space, you have more of this vacuum-like energy. Over time, matter becomes less dominant. Dark energy becomes more important. According to NASA's overview of dark energy, the expansion of the universe began speeding up roughly 9 billion years after the Big Bang, driven by this still mysterious component. That means the universe spent billions of years under one kind of cosmic rule, where gravity shaped and slowed expansion, and then entered an age where dark energy began to dominate the future. This is the world we live in now. We are not in the early universe anymore. We are not even in the simple middle chapter. We are living after the acceleration has already begun. That matters because it changes what the word huge means. The enormous universe we see is not a static palace filled with distant rooms waiting to be explored. It is more like a landscape where the farthest roads are being pulled away while we are still learning how to walk. A galaxy that is visible tonight is not necessarily reachable forever. Its ancient light can still be arriving because it left long ago when the separation between us and that galaxy was different. But light it emits now may be fighting a different cosmic environment. The expansion between here and there may eventually stretch its path so severely that it never arrives. This is one of the most difficult truths to feel. The sky contains objects that we can see as they were, but can never influence as they are. A telescope is not a telephone. It receives old messages. It does not guarantee a future conversation. Imagine standing at the edge of a river that is widening as it flows. On the other bank, someone lights a lantern. The light reaches your eyes, so you know the person exists. You can describe the color of the flame. You can measure the distance to the bank at the moment the light began its journey. You can build a beautiful map. But while the light is crossing, the river widens. The water becomes faster. The opposite bank is still visible, but a boat launched now may never make it across. Cosmic expansion is not exactly a river, but this picture catches the emotional shape of the problem. Seeing something is not the same as being able to reach it. Knowing something exists is not the same as sharing a future with it. The observable universe is full of such places. The number people often hear is about 93 billion light-years across for the observable universe. That does not mean the universe is 13.8 billion light-years wide, even though the universe is about 13.8 billion years old. The reason is that, while light was traveling toward us, space itself continued expanding. The regions that emitted the oldest light we can see are now much farther away than 13.8 billion light-years. This is already enough to confuse the mind. Light had a finite travel time. Space changed during that travel time. So, the distance to the source now is not the same as the time the light spent crossing the universe. The cosmic microwave background is the clearest example. It is the oldest light we can observe directly. It was released when the universe became transparent, roughly 380,000 years after the Big Bang, when electrons and nuclei combined into atoms and the cosmic fog cleared. That light has been traveling ever since, stretched by expansion from a hot glow into faint microwave radiation. When we map it, we are not seeing a wall in space. We are seeing a wall in time. We are looking as far back as light can show us, to the surface from which the first freely traveling photons began their long journey. Beyond that, the earlier universe was opaque to ordinary light. We need other messengers, other theories, and other observations to infer what came before. So even our best cosmic map is not a complete map of existence. It is a map of what has had time to reach us. And as the universe accelerates, the boundary between what can eventually reach us and what never will becomes more important. Cosmologists distinguish between different horizons. There is a particle horizon, which marks the limit of what we can observe, because light has only had a finite amount of time to travel since the beginning. There is also an event horizon, which concerns the future. The limit beyond which events occurring now can never send signals that reach us, no matter how long we wait. That second horizon is the one that makes the future feel closed. It says there are galaxies whose old light is inside our sky, but whose present and future are already causally disconnected from ours. If a star explodes there tomorrow, there may be no tomorrow from our point of view, not because the explosion fails to happen, but because the signal can never cross the growing space between us. The universe has become large enough, and its expansion has become fast enough, that some events are permanently private to their own regions. This is not science fiction. It is a direct consequence of an accelerating cosmos, and it means the universe is huge for a reason that is more disturbing than simple scale. It is huge because the same laws that allowed it to cool, form galaxies, and give time for chemistry also created separations that become absolute. The size is not only the result of cosmic history, it is part of the machinery of cosmic isolation. Now we should be careful. Not everything is being torn away from everything else. Gravity still matters. The moon is not drifting away because dark energy is pulling it from Earth in some dramatic way. The planets are not being ripped out of the solar system. The stars inside the Milky Way are not being carried away from one another by cosmic expansion. Galaxies inside clusters can remain gravitationally bound. On small and medium cosmic scales, gravity wins. The solar system is a bound system. The Milky Way is a bound galaxy. The local group, which includes the Milky Way, Andromeda, Triangulum, and many smaller galaxies, is bound strongly enough that it does not simply expand apart with the universe. In fact, Andromeda is moving toward us. In several billion years, the Milky Way and Andromeda are expected to merge, not because expansion failed everywhere, but because local gravity dominates over expansion inside our neighborhood. This is an important distinction. The universe is not a uniform wind pushing every object away from every other object. It is more like a vast competition between binding and stretching. Where matter has gathered densely enough, gravity can hold structures together. Where the universe is thin and wide, expansion controls the long-term story. This is why the cosmic web looks the way it does. Matter is arranged in filaments, walls, clusters, and enormous voids. Galaxies do not fill space evenly, like dust in a box. They gather along gravitational structures, leaving huge empty regions between them. The large-scale universe looks a little like foam, with bright galaxies tracing boundaries around dark emptiness. That web formed because tiny density differences in the early universe grew under gravity. Regions with slightly more matter pulled in more matter. Regions with slightly less matter became emptier over time. Dark matter played a central role, providing the gravitational scaffolding on which ordinary gas could fall and later form stars and galaxies. But dark energy changes the future of that web. The densest knots remain bound. Galaxy groups and clusters can survive as islands, but the empty spaces between large structures widen. The filaments become more separated. The universe becomes less connected on the grandest scales. Over immense time, each gravitational island will see the others fade. This is one of the most haunting predictions in cosmology. A future civilization living in our merged local group may look into the night sky and see mostly local stars. The distant galaxies that fill our deep field images today may have redshifted beyond detectability. Their light may be stretched into wavelengths too long and too faint to measure. The cosmic microwave background itself will also continue cooling and stretching, becoming harder to detect. The evidence that revealed the expanding universe might become almost impossible to find. Future astronomers, if they arise trillions of years from now, may live inside a dark island and conclude that their galaxy is almost all there is. They might not know about the billions of galaxies we can see today. They might not know the universe was once bright with evidence. The terrifying part is not only that the universe is huge, it is that our current age may be unusually fortunate. We live at a time when the cosmic microwave background is still measurable, distant galaxies are still visible, star formation still happens, and the large-scale structure of the universe can still be reconstructed. We are not at the beginning, but we are also not in the deep cosmic night. We live in a brief observational window, long after the first stars, but long before the universe becomes almost unreadable. That gives our moment a strange urgency. The universe is not only a place, it is a changing archive, and some of its pages are slowly becoming unreachable. This is where the phrase "for a reason" needs to be treated carefully. The universe is not huge because it wanted to scare us. It is not huge because it had a plan, at least not in any scientific sense we can test. When we say the universe is huge for a reason, we are not talking about intention. We are talking about consequence. The universe has the size it has because of the rules it followed from the first moments onward. Expansion, inflation, gravity, radiation, dark matter, dark energy, and time all contributed. Change any one of those ingredients, and the universe could look radically different. If expansion had been too slow, gravity might have pulled everything back together before galaxies, planets, and life had enough time to develop. If expansion had been too fast in the wrong way, matter might have thinned out too quickly for galaxies to form at all. If density fluctuations in the early universe had been much smaller, the cosmos might have remained almost perfectly smooth, with no stars, no planets, no chemistry-rich worlds. If those fluctuations had been much larger, the universe might have collapsed into black holes and violent structures too quickly. If dark energy had dominated much earlier, it might have prevented the growth of galaxies. If it were much weaker or absent, the future would be different, perhaps slower, perhaps more connected, perhaps eventually collapsing depending on other conditions. The universe we see is not random in the sense of being structureless. It is a delicate outcome of competing tendencies. Gravity pulls matter together. Expansion pushes distances apart. Radiation carries energy. Cooling allows atoms to form. Dark matter gathers invisible scaffolding. Ordinary matter falls into that scaffolding and lights up as stars. Dark energy eventually changes the tempo of the entire cosmic dance. The result is a universe large enough to contain billions of galaxies, old enough for heavy elements to form, sparse enough for stable systems to survive, and expanding enough to create permanent horizons. That combination is not simple. It is why the scale of the universe is not merely decorative. The size is part of the story that made complexity possible. A tiny universe would be a very different place. If all matter were squeezed into a much smaller cosmic volume for too long, stars and galaxies might interact violently. Radiation backgrounds could be stronger. Gravitational encounters could disrupt planetary systems. Stable, quiet regions might be rare. A universe that expands and cools creates separation. Separation allows galaxies to become their own environments. It lets stars live for billions of years without constant catastrophic interference from nearby massive structures. It lets planetary systems settle. It lets chemistry proceed on small worlds around ordinary stars. Distance is not only emptiness. Distance is also protection. The same voids that make the universe feel lonely also help preserve order. The same expansion that carries galaxies away also allows heat to dilute. The same cooling that made the cosmic microwave background faint also allowed atoms, molecules, stars, planets, and eventually life. So the universe's size is not just a terrifying fact stacked on top of existence. It is woven into the conditions that allow observers to exist at all. This is one of the strange reversals of cosmology. The vastness that makes us feel insignificant may be connected to why we are here to feel anything. But we do not need to repeat that thought as comfort. It is not simple comfort. It is more like standing in a machine so large that the same gears that made your life possible also make most of reality unreachable. That is a different kind of awe. Not warm, not cruel, just enormous. Let us bring this down from abstraction. Think about our nearest large galactic neighbor, Andromeda. It is about 2.5 million light years away. That means the light we see from Andromeda tonight left before modern humans existed, before agriculture, before language as we know it, before our species had spread across Earth in the way it has now. Andromeda is close by cosmic standards, extremely close. It is part of our local group, and it is moving toward the Milky Way. In the far future, the two galaxies will merge into a larger system, often nicknamed Milkomeda. From the point of view of cosmic expansion, this is a local exception. Gravity is strong enough here to overcome the general expansion between our galaxies. Now compare that with a galaxy billions of light years away. When we see it, we are looking back to a time before the sun was born, or before Earth formed, or before complex life existed, depending on its distance. We are not seeing a neighbor in the ordinary sense. We are seeing a fossil image carried by light, and for the most distant galaxies, the difference becomes even more extreme. A galaxy discovered by the James Webb Space Telescope at very high redshift is not just far away in space. It is far away in time. It belongs to an early chapter of cosmic history, when galaxies were young, stars were forming intensely, and the universe itself was smaller, denser, and different. By now, that galaxy is not where the image seems to place it. The light has taken billions of years to reach us, and during that time, the universe expanded. The source region has moved to a much greater present-day distance. Its current state is unknowable in a direct, immediate way. This is why deep space is also deep time. A telescope is a time machine, but only in one direction. It lets us see the past. It does not let us visit that past, touch it, warn it, change it, or ask it what happened next. The larger the universe is, the more extreme this separation becomes. The night sky is not a live broadcast. It is a layered archive of delays. The moon is about 1.25 light seconds away. The sun is about 8 light minutes away. Neptune is several light hours away, depending on orbital positions. The nearest stars are years away. The center of the Milky Way is tens of thousands of years away. Nearby galaxies are millions of years away. Deep field galaxies are billions of years away. Every direction is a stack of different times. This means there is no single cosmic now that we can see. There may be a way to define time mathematically in cosmological models using the average rest frame of the universe, but observationally, our sky is a mixture. It is not one moment. It is a museum of moments, arranged by distance and by the speed of light. That fact alone would make the universe strange. But the expansion makes it stranger. Because the farther we look, the more we are also looking into a universe whose scale has changed during the travel of the light. A distant galaxy's image is not merely old. It has been stretched, reddened, dimmed, and delayed by the growth of space. This is why the huge universe feels different from a huge room. In a huge room, distant objects are still in the same present with you. You can point across the room and say the chair over there exists right now in a simple way. In the universe, distance breaks that simplicity. The farther away something is, the less the word now behaves like it does in daily life. At cosmic scale, seeing becomes archaeology, and the size of the universe turns reality into a layered excavation. The next part of the terror is emptiness, not darkness, not danger in the action movie sense, emptiness. When people imagine the universe being huge, they often imagine it being filled with things, stars everywhere, galaxies like glowing cities, nebulas like painted clouds, planets waiting in every direction. And in one sense, that is true. The universe contains an unimaginable number of objects. But by volume, the universe is mostly nothing. The distances between stars are enormous compared with the stars themselves. The distances between galaxies are even greater. The voids between galaxy filaments can stretch across tens or hundreds of millions of light years. If the Milky Way were shrunk to the size of a city, the nearest large galaxies would still be far beyond the city limits. If the sun were shrunk to a grain of sand, the nearest star would be miles away on the same scale. Space is not packed, it is diluted. This dilution is not an accident. It is part of the history of expansion. As the universe grew, matter spread out. Gravity gathered some of it into structures, but expansion left immense volumes nearly empty. The cosmic web is impressive precisely because it is surrounded by so much absence. The Bode's void is one famous example, a huge region of space with far fewer galaxies than average. It is not completely empty, but compared with the cosmic web around it, it is a vast underdense region. If the Milky Way were located near the center of such a void, our early astronomers might have seen far fewer galaxies in the sky. Our understanding of the universe could have developed very differently. This is another way the universe's size affects knowledge. Where you are located matters. When you are inside a galaxy, surrounded by stars, orbiting a stable star, with enough time to build instruments, the universe can become readable. If you are in the wrong place or the wrong era, the evidence changes. The universe does not present the same face to every possible observer. From a planet deep inside a dusty region of a galaxy, the broader cosmos may be hidden. From a planet in a future isolated galaxy, the larger universe may be almost invisible. From a world near the center of a violent galaxy cluster, the sky might be bright and dangerous. From a rogue planet drifting between stars, there may be no sunrise, no constellations familiar enough to guide imagination, only distant points of light and a cold background. The universe is huge, but it is not equally accessible from every place within it. That may be one of the reasons the subject feels so powerful for a channel like this. Because the terror is quiet. It does not need monsters. It is enough to understand that most of the universe is not a destination. It is separation. It is silence. It is dark volume between the rare islands where matter has gathered and warmed. Even inside galaxies, the stars are not close in any human sense. Our fastest spacecraft would take tens of thousands of years to reach the nearest stars, if aimed in the right direction and if they survive the journey. A human lifetime is not shaped for interstellar distance. Civilization itself is young compared with a light crossing time to even modest cosmic targets. And beyond the galaxy, the problem becomes absurd. A journey to Andromeda at ordinary spacecraft speeds would outlast species, continents, and perhaps the stability of climates. A journey to distant galaxy clusters is not just difficult. Under accelerating expansion, many destinations are beyond the category of possible. This is why scale is not a backdrop. It is a boundary condition. It defines what kinds of stories the universe allows. Now consider the role of light. Light is the fastest messenger the universe allows, at least according to the physics we have tested. It carries information from stars, galaxies, explosions, black holes, and the early universe. Without light, astronomy would be almost impossible. But light also reveals the cage. Because light has a speed, the universe has horizons. If information could travel instantly, the size of the universe would still be impressive, but not as isolating. We could, in principle, know what is happening everywhere at once. Distance would be inconvenient, not fundamentally separating. But the speed of light turns distance into delay, and expansion turns delay into loss. A photon crossing intergalactic space does not age in its own frame in the usual way. But from our point of view, it can travel for billions of years. During that journey, the wavelength stretches with the expansion of space. Visible light can become infrared. Infrared can become microwave. Microwave radiation can be stretched toward radio wavelengths. Energy does not arrive the way it began. The universe edits the message while carrying it. This is what redshift tells us. For nearby objects, redshift can be caused by ordinary motion. A star moving away has its light stretched. A star moving toward us has its light compressed. But at cosmological distances, redshift mostly reflects the expansion of space itself. The light has been stretched by the growth of the universe during its journey. This stretching is not just a color change, it changes detectability. A galaxy whose ultraviolet light is shifted into infrared becomes invisible to telescopes that only see visible light. A faint source becomes fainter. A signal that once carried high-energy photons arrives softened by the expansion of the cosmos. This is one reason the James Webb Space Telescope was built to observe infrared light. It can see ancient galaxies whose light has been stretched out of the visible range. It is not simply a stronger version of the human eye. It is designed for a universe that has expanded. In a sense, Webb is a machine built to chase stretched light. But even such machines have limits. There will always be signals too faint, too redshifted, too blended with foreground noise, or too delayed to recover. Better telescopes widen the window, but they do not remove the horizon. That is why the universe being huge is terrifying in a scientific way. It gives us evidence, but it never gives us everything. Every observation is framed by what light was able to do. Every cosmic image is a success surrounded by absence. When we look at a deep field, we see thousands of galaxies in a patch of sky that looks empty to the eye. It feels like the universe opening itself. But hidden inside that beauty is the opposite truth. For every photon captured, there are histories we will never receive, surfaces we will never resolve, planets too faint to image, signals too weak to separate, and regions whose future is already outside our causal reach. The larger the universe is, the more severe this imbalance becomes. Knowledge grows, but the unknown grows around it faster than our intuition expects. This does not make science hopeless. It makes science more remarkable. A small amount of light, interpreted carefully, can reveal staggering amounts of reality. From spectra, we learn what stars are made of. From redshift, we measure expansion. From tiny ripples in the cosmic microwave background, we infer the seeds of galaxies. From gravitational lensing, we map invisible mass. From supernovae, we discover cosmic acceleration. But the method itself reminds us of the limitation. We are not standing outside the universe reading a complete blueprint. We are inside the universe, catching old light as it passes by. That is a very different position, and it is the only position we have. There is another reason the universe's size matters. It creates probability. A small universe with only a few stars might never produce a planet like Earth. It might never produce the right chemical history, the right stable orbit, the right mixture of elements, the right long-lived star, the right sequence of accidents. A huge universe gives rare things room to happen. This is not proof that life is common. It is not even proof that life exists anywhere else. But it changes the scale of the question. The Milky Way alone contains hundreds of billions of stars. Many of those stars have planets. Across the observable universe, the number of galaxies is enormous, and each galaxy can contain millions, billions, or even trillions of stars depending on its size. If life is rare, a vast universe may still contain many living worlds. If intelligent life is much rarer, the universe may still have produced it more than once. But the same size that makes life statistically more plausible also makes contact harder. This is the cruel symmetry. A huge universe may be generous with chances and merciless with communication. It can create many islands and place oceans between them that no signal can cross in time. This connects with the Fermi paradox, the famous question of why, if the galaxy or universe contains many possible sites for life, we do not see clear evidence of other civilizations. There are many proposed answers. Life might be rare, intelligence might be rare, technological civilizations might not last long, interstellar travel might be harder than optimistic models assume. Civilizations might not want to broadcast. We might be looking in the wrong ways. Or the galaxy may be full of signals too weak, too brief, or too strangely encoded for us to recognize. But cosmic scale adds a simple pressure to every answer. Distance makes silence easy. Even if a civilization existed 1,000 light-years away, conversation would be painfully slow. A signal sent today would arrive in 1,000 years. A reply would return after another 1,000. That is not a conversation in any human sense. It is more like archaeology conducted between living worlds. At 10,000 light-years, the delay becomes longer than recorded human history. At 1,000,000 light-years, the delay becomes longer than the time since early humans began making many of the tools we associate with our deep past. At 1,000,000,000 light-years, contact becomes almost meaningless for any civilization that changes over normal biological or cultural timescales. The universe may contain other minds, but size means they do not share our present, they share physics. They share the same cosmic history in a broad sense, but they may not share an era that allows exchange. This makes the huge universe feel different from a crowded room. It could be filled with life and still feel empty. It could contain intelligence and still give each intelligence a sky that appears silent. That possibility is more disturbing than a universe with no one else in it. A dead universe is lonely because nothing answers. A universe full of unreachable islands is lonely because something might answer, but the structure of reality prevents the meeting. Again, we do not know which case is true, but the size of the universe ensures that the question is not simple. The cosmic scale that makes wonder possible also turns wonder into distance. The future deepens the problem. Stars are not permanent. Galaxies are not permanent in the way they appear when photographed. They evolve, collide, exhaust gas, form fewer new stars, and slowly change their populations. The universe has already passed its peak era of star formation. Long ago, galaxies formed stars at a much higher rate than they do today. The cosmos was more active, more crowded with young stellar fire, more chemically restless. Today, many galaxies still form stars, including the Milky Way, but the overall cosmic rate has declined. In the far future, the easy fuel will run low. Gas will be locked into stars, stellar remnants, planets, and black holes. New stars will form more slowly. Massive stars will die quickly. Smaller red dwarfs will continue burning for trillions of years, providing the longest-lived ordinary light in the universe. Eventually, the age of bright stars will fade. This is not something we need to fear in a human timescale. It lies far beyond any ordinary future we can imagine. But cosmology forces the mind to follow consequences beyond comfort. The universe being huge means it also has room for time to become enormous. Spatial scale and temporal scale mirror each other. The distances are too large for our bodies. The times are too long for our stories. In the very far future, the merged local group may be one of the few visible structures for any observers still around. Distant galaxies will have slipped beyond the cosmic event horizon. The night sky may no longer contain the evidence that taught us about cosmic expansion. The cosmic microwave background will be stretched to wavelengths so long and temperatures so low that detecting it may become extraordinarily difficult, perhaps practically impossible for civilizations using methods like ours. This idea is almost tragic. The universe will not only become darker, it may become less explainable from inside. The clues will fade. A future astronomer could be brilliant, careful, and curious, yet lack the evidence available to us. They might live under a sky with fewer visible galaxies. Their local stars might dominate everything. They might conclude that the universe is static, isolated, or much smaller than it really is. Truth would still exist, but the accessible evidence would be poorer. This means our era is not just one random moment. It is a moment when the universe is old enough to contain rocky planets, heavy elements, stable stars, and observers, but young enough that the large-scale cosmos can still be seen. That is a narrow kind of timing, not narrow in years because the window lasts billions of years, narrow in cosmic meaning. Too early, and there are no heavy elements for planets like Earth. Too early, and the universe is too hot, too violent, too young. Too late, and the evidence of the wider cosmos fades beyond reach. We live between those extremes. The universe is huge, but not yet silent to our instruments. It is expanding, but not yet hidden from our maps. It is ancient, but not yet exhausted. That may be why studying it feels so strange. We are late enough to look back. We are early enough to still see far. This timing does not make us central. It makes us temporary witnesses, and perhaps that is more powerful. A central observer imagines the universe arranged around them. A temporary witness understands that the view itself is passing. Now let us return to the title. The universe is huge for a reason, and it's terrifying. The reason is not one thing. It is not only inflation. It is not only expansion. It is not only dark energy. It is the combined result of a cosmic story in which space stretched rapidly, matter cooled, gravity gathered structure, stars forged elements, galaxies arranged themselves into a web, and a mysterious acceleration began shaping the future. Each part of that story matters. Inflation explains why the early universe could become so smooth and so vast, beyond what simple light travel would suggest. Expansion explains why distant regions separate and why old light arrives stretched. Gravity explains why the universe is not a featureless mist, but a structured place filled with galaxies, clusters, filaments, and voids. Dark matter explains why galaxies and clusters had enough invisible gravitational framework to grow the way they did. Dark energy explains why the future is not just expansion, but accelerated separation. Time explains why all of this could become layered into the sky we see now. So the universe is not huge as an afterthought. Its hugeness is part of the chain of events that made the cosmos what it is. And the terrifying part is that the same chain leads to limits. The universe became big enough to allow complexity, but too big to fully know. It became old enough to produce observers, but old enough that its earliest light is already stretched into a cold background. It became structured enough to form homes, but sparse enough that those homes are separated by almost impossible distances. It became readable enough for science, but not transparent enough to reveal everything. It became dynamic enough to evolve, but dynamic enough to carry galaxies beyond reach. Notice how different this is from the simpler fear of space. It is not just that you would freeze or suffocate or be struck by radiation without protection. Those dangers are real, but they are local. The fear here is architectural. It is built into the arrangement of the universe. You can build better spacesuits. You can build stronger rockets. You can shield against radiation. You can cross oceans, climb mountains, leave planets, and perhaps one day reach nearby stars. But no engineering project can make the entire universe mutually reachable if cosmic expansion forbids it. That is a different category of limit. A technological limit invites progress. A physical horizon defines the rules of the game. This does not mean exploration is meaningless. It means exploration is more precious. The reachable universe is not small in any human sense. Even the Milky Way alone contains more worlds than we could study in countless generations. Nearby galaxies, if ever reachable through methods beyond anything we possess now, would represent an unimaginable expansion of possibility. The local universe is vast enough to humble every ambition. But it is not everything, and no honest account of cosmic scale should pretend that patience alone unlocks the whole map. Some doors are not locked. They are receding into a future where the concept of opening them no longer applies. There is a final layer to this. When people ask why the universe is so big, they often expect the answer to make the universe feel more understandable. And in one way, it does. Cosmology gives us a framework. The universe expanded from a hot, dense early state. It cooled. It became transparent. Structures formed. Stars lit up. Heavy elements were made. Planets formed. Life appeared on at least one world. The expansion continued. Dark energy became important. The future began leaning toward isolation. That is a story. It has sequence. It has causes. It has evidence. But understanding the sequence does not make the scale feel ordinary. It may make it feel stranger, because now the vastness is not a vague mystery. It is measured. It is mapped. It is supported by data. We know enough to realize that our intuition is not built for the arena we inhabit. Human beings evolved to understand landscapes, weather, animals, rivers, faces, fire, seasons, and the motion of the sun across the sky. We are good at distances that can be walked, times that can be remembered, dangers that can be heard in the grass. The universe asks us to think in billions of years, billions of galaxies, light that travels for longer than planets have existed, and futures in which entire cosmic structures vanish beyond horizons. No wonder the mind reaches for simple phrases: huge, empty, terrifying, beautiful. But the real story is more specific than any one of those words. The universe is huge because expansion is one of its basic facts. It is huge because the early universe may have inflated faster than ordinary intuition can picture. It is huge because light has had time to cross only part of it. It is huge because the visible part is not the whole. It is huge because the future is stretching the cosmic web into isolated islands. And it is terrifying because size here is not passive. Size decides causality. Size decides visibility. Size decides whether two events can ever become part of the same story. On Earth, distance feels negotiable. A place is far away until someone builds a road, a ship, an airplane, a radio tower, an internet cable. Human history is partly a story of shrinking distances. The universe refuses to shrink all the way. It lets us improve our reach, then shows us a horizon beyond improvement. This is why the subject can feel almost personal, even though it is not. The universe is not trying to hide from us. It has no need to try. Its structure is enough. Space expands. Light takes time. Energy fades. Gravity binds locally. Dark energy separates globally. From those plain statements, the grand loneliness follows. Still, the story should not end only in fear. Not because fear is wrong, but because fear alone is incomplete. There is something extraordinary about the fact that any of this can be known. A species on one planet, orbiting one ordinary star inside one spiral galaxy, can measure the temperature of radiation released when the universe was only a few 100,000 years old. It can detect elements in stars thousands of light years away. It can infer invisible matter from gravitational effects. It can notice that distant supernovae are dimmer than expected and realize that the expansion of space is accelerating. That does not erase the horizon. It makes the horizon more meaningful. We cannot see everything, but we can understand why we cannot see everything. We cannot reach every galaxy, but we can calculate why some galaxies are unreachable. We cannot watch the beginning directly, but we can study the oldest light and the patterns left in matter. The universe did not give us a complete view. It gave us evidence. And evidence, handled carefully, can become a bridge across scales that bodies can never cross. This is the quiet triumph inside the terrifying vastness. Not that we conquer the universe, not that we stand above it, but that we are part of it and still able to ask what kind of universe it is. The atoms in our bodies were made in stars. The planet beneath us formed from material enriched by earlier generations of stellar death. The light entering our telescopes has traveled through the same expanding space that carries galaxies away. We are not separate from the cosmic process we are trying to understand. We are one of its late consequences, a small, temporary thinking consequence. That may sound poetic, but it is also physically true. The calcium in bones, the iron in blood, the oxygen we breathe, and the carbon in every living cell came from cosmic chemistry. The universe had to be old enough and large enough for those elements to be made, scattered, gathered, and built into planets. A smaller or younger universe might not contain us. A very different universe might contain no stable stars, no rocky planets, no long chemical experiments, no quiet skies above oceans. So when we say the universe is huge for a reason, the deepest answer may be this. A universe capable of producing complexity may need vastness, time, cooling, separation, and structure. But once it has those things, it also has horizons, silence, and unreachable depths. The gift and the terror come from the same source. The scale that permits life also prevents complete knowledge. The distance that protects worlds also isolates them. The expansion that cooled the early fire also carries galaxies away. This is not a contradiction. It is the shape of our reality. There is also a practical lesson hidden inside all of this. When astronomers choose what to observe, they are not only choosing targets, they are choosing which parts of cosmic history are still reachable by evidence. A nearby star can be studied in detail. Its planets may tug on it. Their atmospheres might one day reveal chemical traces. A distant galaxy can be measured more faintly through redshift, brightness, shape, and spectrum. The cosmic microwave background can be mapped as a surface of ancient radiation. Each layer of distance demands a different method. The larger universe forces science to become creative. We use parallax for nearby stars, standard candles for greater distances, redshift for cosmic expansion, gravitational lensing for hidden mass, and background radiation for the early universe. No single ruler spans the entire cosmos by itself. The cosmic distance ladder is built step by step, each rung checked against another because the universe is too large for one simple measurement. This is important because it shows that vastness does not defeat knowledge all at once. Instead, it changes the kind of knowledge available. The closest objects give detail. The farthest objects give history. The early universe gives patterns rather than photographs. The future gives predictions rather than direct evidence. A complete script of the cosmos would require all of these forms at once, and we still would not have the whole. That is not a flaw in astronomy. It is the condition astronomy works under. Every science has limits, but cosmology studies the largest possible limit, the boundary of what the universe can reveal from one location inside itself. The more we learn, the clearer that boundary becomes. The edge of knowledge is not a foggy line that disappears when instruments improve. Some parts do move outward with better tools, but other edges are written into causality. Better mirrors, colder detectors, longer exposures, and more sensitive surveys can gather more of the available light. They cannot gather light that never arrives. This is why the huge universe teaches humility without asking for surrender. We can learn astonishing things. We cannot learn everything. Both statements are true at the same time. So, imagine the universe one last time, not as a picture on a screen, but as the largest history there is. In the beginning, it was hot, dense, and opaque. Then it expanded. For a brief and mysterious instant, it may have inflated with astonishing speed, stretching tiny quantum fluctuations toward cosmic significance. It cooled enough for light to travel. Dark matter gathered into invisible structures. Gas fell inward. The first stars ignited. Galaxies grew. Some stars died and enriched space with heavier elements. New stars formed with rocky planets around them. On at least one of those planets, oceans persisted. Chemistry became biology, and biology eventually built instruments to look back into the darkness. By the time those instruments opened their eyes, the universe was already enormous. The oldest light had stretched into microwaves. Distant galaxies were racing away with the expansion of space. Dark energy had begun shaping the future. The observable universe was only a portion of whatever exists beyond the horizon. And the more carefully we measured, the more we learned that the horizon is not just a failure of technology. It is a feature of the cosmos. That is the terrifying truth hidden inside the word huge. The universe is not a giant room we have not fully explored yet. It is a changing space-time with regions that can never exchange signals, eras that erase evidence, and distances that turn present reality into unreachable history. But it is also the only universe we know. It is the place that made every star, every planet, every ocean, every living cell, every thought, every question, and every telescope pointed into the night. Its size does not make our questions meaningless. It makes them rare. For a short time, in a galaxy that will not always have this view, on a planet that will not last forever, minds can look outward and recognize the scale of the thing that made them. That recognition may not change the universe. It does not slow dark energy. It does not bring unreachable galaxies back. It does not turn the cosmic horizon into an open road, but it changes what the darkness means to us. Without understanding, the night sky is only distance. With understanding, it becomes history. It becomes physics. It becomes a record of expansion, fire, cooling, gravity, loss, and time. And maybe that is the final reason this subject stays with us. The universe is huge enough to make us feel almost impossibly small. But it is also huge enough to have produced beings capable of noticing that smallness. It hides most of itself beyond time and distance. Yet the part we can see is enough to reveal a story grander than anything our ancestors could have imagined. A story where the same expansion that created room for galaxies also pulls those galaxies away. Where the same darkness that frightens us preserves the ancient light. Where the same vastness that isolates us made it possible for one small world to exist long enough to wonder why. And that is why the universe is huge for a reason. Not because it was made for us, not because it owes us an answer, but because its vastness is the consequence of the deepest processes we can observe, and those processes made both our existence and our limits possible. The reason is written into expansion, the terror is written into the horizon, and the beauty, if we are allowed to call it that, is that for this